どうぞよろしくお願いいたします。
Good afternoon, everyone. I am Daryl Ui.
I am Yosing Yi.
And I am Justin Sim, and we are students from Hwa Chong Institution in Singapore.
So this is a map of the Asia region, and we are now in Japan, which is there. And Taiwan is located a bit southwest, while Singapore is near the bottom of the region, there. So Singapore is about 719 square kilometers large, and it has around 6 million people. So if we compare it to Japan, it's 526 times larger, but its people is 21 times of Singapore. Hence, you can see that Singapore has more people per unit area compared to Japan.
Speaking of people living closely together, Singapore has people of many different races, notably the Chinese, the Malays, the Indians, and the Tamils. As a result, Singapore is a multiracial and multicultural society where people are living together in harmony despite their backgrounds.
So with people of many different races living together, there are also many different kinds of food in Singapore. Here are some of the delicious foods you can find in Singapore.
In fact, we get a little crazy about food, that one of our buildings is modeled after a fruit. So we call this the Esplanade Theatre, where many concerts are held there every year, and it's modeled after the durian, which is dubbed the king of fruits, and is found in the Southeast Asia region. So Singapore also has many interesting structures. You can see the Merlion over there, which is known as the icon of Singapore, and consists of the head of a lion and the tail of a fish. In the picture, you can also see the Marina Bay Sands, where it looks like a boat that's supported by 3 buildings, and the Singapore Flyer on the left.
Singapore is a clean and green city, and our school is no exception. Our school will be celebrating its 100th anniversary in 2019, which is 2 years from now. And we are under the integrated program, which means that we spend all 6 years of our high school, junior high school, and senior high school education in the same school. And as a result, we have a total of over 4,000 students in the school.
We will now present to you our research titled Novel Cobalt-3 Complexes Incorporating Amino Acid Reduced Sheaf Bases.
So, cobalt complexes can undergo selective transitions between the +2 and +3 oxidation states. It also contains certain redox properties that are unobserved in other transition metal species, and is compatible with the human body in, for example, the vitamin B12, where you can see the cobalt central ion over there. So we decided to use reduced sheaf bases because we found that copper-2 amino acid reduced sheaf base complexes can display various biological properties. However, for cobalt amino acid reduced sheaf base complexes, it's not yet been reported on.
For our reactions, we have first synthesized 2 cobalt-3 starting materials based on previous literature. This is starting material 1, which was synthesized by oxidizing of commercially available red cobalt-2 nitrate. We obtained a violet-colored cobalt-3 complex, which was our starting material 1, and the structural formula can be seen as above. Following that, we also synthesized starting material 2 with a similar procedure, and this is its structural formula. In order to react with our starting materials, we have also synthesized 3 species of phenol-reduced sheaf bases. This was also done based on previous literature and incorporates a 2-step process. In the first step, 2-hydroxybenzaldehyde was reacted together with an amino acid. In this case, we used either glycine, alanine, or valine in order to obtain a sheaf base. The color change of this reaction was noted to be from colorless to yellow. Following that, we reduced the sheaf base using sodium borohydride in order to obtain our reduced sheaf base. The color change was noted to be from yellow back to colorless. The colorless solution was then allowed to crystallize in order to obtain white solids, which was our reduced shift base.
So firstly, we reacted both of our cobalt-3 starting materials with the reduced shift bases in water. However, we found that our reduced shift bases have a low solubility in water, and that also after the reactions were completed, we obtained a combination of brown oils and black solids. And we suspected that the products had decomposed in water. Hence, we decided to use a mixture of organic solvents and water, which included ethanol, acetone, and dimethyl sulfur oxide. However, in the end, we still obtained the same products of brown oils and black solids.
Hence, we decided to use another form of reduced shift bases. This time, we reacted two pyridine carboxaldehyde with valine and alanine to form our pyridine reduced shift base. The color change for this synthesis was similar to that for the synthesis of our phenol reduced shift bases. We found that the pyridine reduced shift base could dissolve in water better compared to the phenol reduced shift base. Hence, we reacted both our cobalt starting material with the pyridine reduced shift bases in water, while nitric acid was added for the reactions involving starting material 2. Red solutions were obtained for all the reactions.
The color change for the reactions was observed using ultraviolet visible spectroscopy. The shift in the peaks in the spectrum corresponds to the change in color for our reactions involving starting material 1, which was from pink to red. From the red solutions which we obtained from the reactions involving valine pyridine reduced shift base, we also obtained red crystals, which we have sent for characterization. We first confirmed the structure of our product through X-ray crystallography. We found that both the crystals from the reactions incorporating starting material 1 and starting material 2 had the same structure. Also, a nitrate counter ion was present alongside the complex in the structure.
We also sent those red crystals that we obtained from the reaction for mass spectrometry, and the result indicated similar mass spectra for the red crystals, where the species with the highest abundance had a mass overcharge ratio of 473, which corresponds with the formulation of our expected compound. So from these two characterization methods, we concluded that our reduced shift base acts as a tridentate ligand and binds to our cobalt-3 central ion in a 2:1 ratio.
We also sent our crystals for proton nuclear magnetic resonance, and this is the spectrum we have obtained. We have been able to match all the peaks in the spectrum with the protons in our compound, which further confirms the structure of our compound. In conclusion, our reactions involving phenol reduced shift bases yielded brown oils and black solids, which we suspected were decomposed products. On the other hand, reactions involving pyridine reduced shift bases yielded red solutions from which red crystals were obtained, and the ratio of the cobalt-3 ion to reduced shift bases were found to be 1:2. For future work, we will complete characterization of our products by sending them for elemental analysis and Fourier transform infrared spectroscopy. We will also be investigating the biological properties of our novel cobalt-3 complexes. We would like to thank the organizers of the Grand Contest in Chemistry for inviting us to share our research with all of you here today. We will be happy to take any questions from all of you. Thank you.
ありがとうございます。それではぜひご質問などしていただきたいと思います。ぜひ高校生の皆さんもよろしければ海外の皆さんにご質問をなさってみてください。では挙手をしていただきたいと思います。ご質問のある方は挙手をお願いします。高校生の皆さんもどうぞ積極的にいかがでしょうか。では先生からお願いいたします。
Thank you for your very nice presentation and including the introduction of Singapore. So I have only one simple question. So usually the cobalt-3 plus compound is inert for the ligand exchange reaction. However, in your case, so the new complex was obtained as a result of the ligand exchange reaction. How do you think?
So we think that the reduced shift bases form stronger bonds with the cobalt compared to the other ligands. So that's why we could obtain a new complex which has not been found before. And we are really excited that we have found such new complexes. Thank you.
ありがとうございます。その他ご質問、では中澤先生、マイクをお持ちいたします。
Thank you very much. Your final purpose is to explore the biochemical properties.
All right.
Okay? And now you studied from the cobalt 2 complex, and then you get the cobalt 3 complex.
No, we do the cobalt 3 complex
So
straight
you
away.
studied from the cobalt 2 and oxidized.
Yeah.
Then you get the cobalt 3 complex,
Yeah.
right?
Yes.
And I guess that if you think about the biochemical activity, cobalt 2 complex might be effective than the cobalt 3 complex because the cobalt 3 complex is usually very, very stable. So why didn't you get the cobalt 2 complex instead of the cobalt 3 complex?
So originally, since we started this project relatively new this year, so before that, this project was actually, we started from another point, which is initially we tried with cobalt 2, but we reacted with the other form of reduced shift base, the phenol one, and we found that it could not work. So we tried at first, we thought that the reduced shift base was not the issue. So we changed the cobalt 2 to cobalt 3. And we reacted first, and then we found that the reduced shift base was the issue. So now we have the cobalt 3. So we'll be trying with the cobalt 2 after we finish characterization for our cobalt 3 complexes.
And then we will continue with we will do a comparison study between cobalt 2 and cobalt 3.
Thank you. And you also identified the X-ray structure. Okay?
Sorry?
You identified the structure by X-ray analysis. Okay? And that complex should have another geometrical isomer. But what you obtained is only that isomer.
Yeah.
Is there any reason that why you obtained this iso structure?
This structure might be one of the. There are many different isomers, so maybe this structure is the one that we received the spectrum for. We will also try to see if we can obtain the other isomer from.
You already obtained the other isomers?
No, we did not.
You did not. So I wanted to the reason why that structure is very stable compared with the other isomer. Okay, let's talk later. Thank you.
ありがとうございます。その他ご質問はございますでしょうか。よろしいでしょうか。はい、辰巳先生お願いいたします。
The following is the question, Professor Nakazawa's question. So you are trying to mimicking the properties of vitamin B12, for instance, right?
No, we just give you an example that
Okay,
cobalt 3 can be a.
Then you see, you have a pyridines coordinate from top and bottom in the structure, pyridine part, pyridine part, pyridine, yeah, right? And then that bond should be weaker than the other ones. Is it true? Because you see, it's cobalt 3, it's octahedral. But when you add electrons, reduce the cobalt to cobalt 2, then there's one or two bonds should be weakened. And where do you know the bonds would be weakened?
We are not so sure on that. I think we can get back to you.
Just a question in chemistry, that's all.
Okay.
ありがとうございます。それではお時間も参りましたので以上とさせていただきます。シンガポールからファーチョンインスティチューションの皆さんでした。どうもありがとうございました。
Thank you.